Today we are going to discuss the standing wave. First, we can ask one question: how the standing wave is formed? Suppose if you are taking this thing like this, so if you are oscillating at the one end, then the wave will propagate from the oscillating end to the fixed end. Here it's a fixed end on the left. After hitting at the fixed end, what will happen means the wave, it will be reflected back. The produced wave is moving from the left to right. After the reflection, the wave hitting on at the end, it will be reflected back. So there are two waves. One is moving from the right to left, another one is moving from the left to right. The reflected wave from the left to right, the produced wave from the right to left. These two waves, it will interfere, it will form the standing wave. So how the standing wave will form means the interference between the interference between two waves forms the standing wave. So, how the standing wave will be characterized? That's our main motive. There are nodal points that will characterize the standing wave. So, here the nodal points are characterized the standing wave. So, what are the nodal points? In the standing wave, we can ask the next question. There are two nodal points. The first nodal point is called the node points on the standing wave. So, what do you mean by the node point means? Suppose if the reflected wave as well as the produced wave, if these two waves, suppose one wave is phase is like this, another wave phase is out of phase with respect to the one wave, then these two waves produce the point of no displacement in amplitude. That means the zero amplitude it will form. It will interfere distinctly. So if the phase between two waves is out of phase or pi. If the phase between the two waves is pi, that means if it is out of phase, the produced interference form node displacement in amplitude this is called nodal point. Nodal point. Suppose if the two waves, the produced wave as well as the reflected wave, the envelope, if it is same phase, then that will form the nodal points. So antinodes. Then second nodal point is antinodes. That means if the one wave phase is like that, the another wave phase is also like that. So it will add up, it will form the resultant amplitude will be large. One is maybe reflected, another one is the transmitted wave. Then how we can define the antinodal point means if the phase between two wave is 0. That means they are identical. If they are identical, the produced interference is constructive and form maximum displacement from the mean position. From mean position, this is said to be antinodal points. So wherever the two waves form the meet with the resultant phase is 0, that means they are identical. In those places, they will form the antinodal points. So how it will be looking like that? Standing wave, how it will be looking like that? The resultant wave after meeting these two waves, here it's fixed range. It will form the standing wave like this. So here in these points are the nodal points. These are the node. Here actually then this here actually the boundary condition. Anyway, the amplitude is 0. Here is the produced. Maybe we are placing the wave here. It's fixed range. This maximum displacement. These points are antinode. Here, this is also antinode. That means in between node and antinode, the two waves are meeting with the difference in phase not 0 or neither the pi. So this is a way to form the standing wave. That means all the points vibrate with the same frequency because we are producing this. Suppose if you are using the if you are producing this wave at 70 Hz, then the points on the string, all of them will vibrate with the same frequency, but the interference from the antinode, nodal, even the nodes looking like the 0 displacement, but the points on the string vibrate with the 70 Hz frequency. Suppose if you are using the 70 Hz tuning fork, if you are producing the standing wave, definitely all the nodes as well as antinode point, and then other those node points it will vibrate with the same frequency, the 70 kHz. So this is the way we can characterize the standing wave. But next question is we can ask how we are going to understand using the mathematics. So that is our next question. So just we have discussed how the standing wave is forming. The interference between the two waves, it will form the standing wave. These waves characterized by the nodal as well as the antinodal points. The right hand side figure shows AN shows the antinodal points where the displacement of the wave is maximum. The nodal points is described by the 0 displacement from the mean position. So here N represents the nodal points. Now using the mathematics, we need to try to understand this figure, right hand side figures. So in general, there are two waves that will form the standing wave. Here one wave we can define, maybe the produced wave you can define y1, maybe that's the first wave. It will be it is as a function of position as well as the time, because we are discussing the one dimensional form, so we are taking y1 as a function of x. So this wave has some amplitude. Maybe I can take the sine function to describe the produced wave sin kx minus omega t. Omega represents the frequency of the angular frequency of the wave. K is a wave number. After reflection, the same wave is traveling but in opposite direction. Again, it is in say x direction but opposite to the incident wave with the same amplitude, because the reflected wave it is identical to the produced wave, so the amplitude will be a with the same wave number, thus in opposite direction. That means it will be plus. It's with the same angular frequency time t. So the resultant wave, it should be equal to y equal to the resultant wave the y as a function of x comma t, it will be equal to, it's a sum of the produced wave y1 x comma t plus the reflected wave y2 x comma t. This is the resultant wave. It will produce the standing wave when they are meeting on the string. So here the y1, it will be equal to a sin kx minus omega t plus the reflected wave a sin kx plus omega t. Now we can use a trigonometry identity. The trigonometry identity is nothing but, here we can define the sin theta 1 plus sin theta 2. Suppose if sum of two sine function, we can write it, it should be equal to 2a. Suppose if the amplitude is attached with the sine function, it will be equal to 2a sin of theta 1 plus theta 2 divided by 2, then cos of theta 1 minus theta 2 divided by 2. So if you are using this trigonometry identity, the resultant wave y of x comma t, it will be equal to 2a sin of the kx minus omega t plus kx plus omega t divided by 2, then the cos of theta 1, here it's nothing but kx minus omega t minus kx minus omega t, because it's a minus theta 2, here theta 1 it's a kx minus omega t, theta 2 is kx plus omega t. So using this identity, we can rewrite the resultant wave like this. So 2a sin of, we can cancel the omega t minus omega t. So 2kx, you can cancel the 2 also. So sin kx. Then the cos, we can cancel the kx minus kx. It will be cos of minus 2 omega t divided by 2. So we have minus omega t. Cos of minus theta is plus cos theta. So simply it's cos of omega t. So the resultant wave y of x comma t, it will be equal to 2a sin kx cos omega t. Here surprisingly, if you are looking at that, the resultant wave is oscillating to the same angular frequency as that of the incident wave as well as the reflected wave. So the frequency of the wave is same on the string, but if you look at the function attached with the frequency, it will be 2a sin kx. So the amplitude of the wave is oscillating as a function of sine. If you look at the right hand side figure, it will be showing that it's a function of the position. The resultant is is with respect to the x, it's a function of position. So the maximum amplitude is here, it will form 2a when the sign argument it goes to pi by 2 or 3 pi by 2, 5 pi by 2. The resultant amplitude goes to 0 when kx is equal to 0, pi or 2 pi. So we are going to discuss how the node as well as the antinodes are forming in the standing wave, how we can define the position, what is the n, how we are going to measure the wavelength. These are the things we are going to discuss. So now the resultant wave is y x comma t equal to 2 times the amplitude sin kx cos omega t. Suppose if you are consider at the boundary here, left boundary, here this is the right boundary. At these two boundaries, if you look at all the waves, there is a zero amplitude. So the boundary condition says at y 0 comma t. Suppose if you are taking the wire, this end is 0, the other end is at L. The length of the wire is here L. So at x equal to 0, the amplitude goes to 0. So if you are substituting in the wherever the x, if you are substituting the 0, k times 0 cos omega t, definitely it goes to 0 because sin 0 0. So it is 2. At x equal to 0, the amplitude of the wave is 0. This is the first boundary condition. The next boundary condition, y at x equal to L comma t equal to 0. That means 2a sin k times the in the place of x we need to replace as L, because now we are going to look at the wave amplitude at x equal to L cos omega t. So here anyway the cos omega t we can make it 0, but sin it can't be 0. So 2a sin kl equal to 0. So here definitely the wave frequency cannot be 0 because we are generating. So cosine function we can't take it as 0. So to satisfy these boundary conditions, we need to take the 2a sin kl equal to 0. Therefore sin kl equal to 0 because the amplitude cannot be 0, or else there is no wave. So we need to take sin kl 0. So the boundary condition says kl equal to n pi, because sin pi goes to 0, 2 pi, 3 pi. So if n equal to 1, 2, 3, 4, 5, all the values, this function goes to 0. So if this condition is true, then at x equal to L, the wave amplitude is 0. Or we can replace, already we know the wave number k equal to 2 pi pi the wavelength lambda. This is a wave number. Just if you are replacing using the k value, 2 pi pi lambda times L equal to n pi, the pi we can cancel. So the wavelength lambda equal to 2L pi n. So one can use this equation to measure the wavelength of the standing wave. What do you mean by n? N is just a number, the 1, 2, 3, 4, 5. So this is said to be the harmonic of the wave. Suppose n equal to 1. If n equal to 1, it's said to be the first harmonic. if n equal to 2, so it is the second harmonic. Here few harmonics are present. The n equal to 1, the first figure shows is first harmonic. That means only one loop. N equal to 2, there are two loops. So suppose you take this equation, if you are plotting, you will get the two loops. So second harmonics. The n equal to 3 says there are three loops in the standing wave. So it's a third harmonic. N is equal to 0 also will satisfy the equation, but we can't take it the 0 harmonic. That means it doesn't mean anything. So we need to take from the n equal to 1 up to n harmonic. We can plot this kind of standing wave. So our resultant wave now becomes y x comma t equal to 2a sin the k. We can replace it by n pi by l times x cos of omega t. So this is now our resultant wave. But we need to identify the position of the node as well as the antinode, because the nodes will form and the two waves interfere destructively. The antinodes will form and two nodes are interfere constructively. So where is the antinode will form? Where is the node will form? That is our main question. But the amplitude at the node position goes to 0. Look at the n. Wherever the n, the amplitude are 0 for the standing wave. Similarly, wherever the an, that is the antinode, the amplitude will be the maximum. So here the maximum amplitude is 2a. Anyway, we are going to measure it. Now, just you can find the position of the node first. The position of the node, the harmonic position of the nodes. So to find the position of the nodes, the amplitude goes to 0. That means at node points, the amplitude goes to 0. So now we are going to look at the node positions. 2a sin of n pi by x divided by l cos of omega t. The amplitude, this is the amplitude with frequency, angular frequency omega, that is close to 0. So anyway, this cannot be equal to 0 because there is a wave, it will oscillate the frequency, it can't be equal to 0. The amplitude can't be equal to 0. The only one function goes to 0, that is a sine function. So to satisfy the right hand side of the equation, the sine n pi by x by l goes to 0. So here what are the value the sine argument should have means it should have the m pi argument n pi by x by l. It should have the m pi value. Then only the nodes at the nodes the amplitude goes to 0. So what are the m values means m0, 1, 2, 3, 4, all the values should be. If m equal to 0, that's the first harmonic, first node position. The m equal to 1, that will determine the second node position. M equal to 2, that will determine the third node position. M equal to 3, that is the fourth node position. So we can determine like that. Now we can cancel this pi. So the position x of the node, that should be equal to m times l divided by n. Here m represents the node number. Here n represents in which harmonic the position we need to find for the nodes. So this is the equation. It's for to find the node position. Suppose take the fourth harmonic. So for example, take the fourth harmonic. That means harmonic n equal to 4. That's the fourth harmonic wave. we can take we need to find the first, second, third nodal position. That means m value equal to 2. So m equal to 2. That is the third nodal position. So if you are finding that value, x equal to m equal to 2, l by n equal to 4. So l by 2. Actually here it will come. This is the starting point is first, so nodal position. This is 2. This is a 3. That means m equal to 0, 1, 2. This is a third nodal position. By default, you can take this from the 0. It's a third nodal position. It's l by 2. So it is satisfying this condition. Like that, you can find for n equal to 3, the third harmonic, we can find the nodal position 2. The second nodal, this is 0, 1, 2. Nodal position you can find. Suppose if you are finding the nodal position, the position x equal to m equal to 2, l by n equal to 3. So 2l by 3. The nodal position should be here. This is the point, 2l by 3. So like that you can find in n harmonic the mth nodal position. You can easily figure it out. Now the next one is we need to find the antinodal position. Of the antinodes. So in the antinodes, the amplitude maybe we can consider we need to take it maximum. That maximum value here we can take 1, because in the resultant amplitude it should be, the resultant rate should be 2a sin n pi by x by l cos omega t equal to, here sine function. We need to find the sine value can have the maximum value plus 1 or minus 1, because it's a harmonic function. So we can take the maximum value of this amplitude, we can take it as 1. Here, anyway, this isn't necessary. We can take only the sine n pi by x, because we are going to find the position of the antinode points. The another two thing, we can make it as like a constant. We can put it into right hand side, because at the antinode points, the 2a is a constant value. Frequency of the wave is constant. So all the concepts observed in the 1. Sin n pi by x by l equal to 1. So what are the value we should have? 1 means equal to, it should be m pi by 2. That means the m value equal to 1 or 3 or 5 or 7. So these are the allowed value for the sine function to have the maximum altitude. Actually, the not 5, because 3 pi by 2 is form minus 1. So pi by 2, 3 pi by 2. Yes, 3, 5, 7. Anyway, in the antinode, suppose if you are taking the antinode, it should be like that. Either it is plus 1 or minus 1. It doesn't matter anything. This maximum we are going to take, it's either plus 1 or minus 1. So the m value antinodal points at 1, 3, 5, 7. The odd numbers are allowed numbers. If we can make it, it's plus or minus 1. Now it's okay. So the position of the antinode we can find, it should be x equal to m l by 2n. Let us take the example. The m value, that means the second antinodal point, for the second antinode, m value equal to 3. We are going to find at the fourth harmonic n equal to 4. Suppose we are finding the position of the antinode at the m equal to 3, n equal to fourth harmonics, the value 3l by 2 times the 4, so 3l by 8. So this is the way we can find the nodal as well as the antinodal point. Suppose m equal to, if you are taking 1, that means the first antinodal in the fourth harmonic, so x equal to 1 L by the 2 times n, so L by 8. So this is where we can find the position of the antinodal points in the earth.